Hey guys, in this video we're going to talk about 1.7 and 1.8, and these two sections in the textbook introduce the idea of a limit and continuous functions. So the first thing I want to talk about continuous functions. So what is continuity is our first question. So intuitively, a continuous function is one that you can draw with your pencil without picking it up. So for example, f of x equals x squared is a continuous function. And the reason intuitively is because we can draw the curve x squared without picking up the pencil, right? So there's no jumps or holes, it's just a continuous curve with no spaces. Likewise, we could have something like this. So this is continuous. Could have something like this. That's continuous. But something like this. So if we have something like, let's say we have maybe the graph goes like this, and then maybe it goes like this. Let's do this again. So maybe we have a graph that looks like this. So this would be an example of a function that's not continuous because we have to pick up our pencil when we're drawing, like when we're finished drawing the left curve, we have to pick up our pencil to draw this curve on the right. So this would be an example of a function that's not continuous. A function is continuous on an interval if its graph has no breaks, jumps, or holes in that interval. So let's talk about what that means. And let's just illustrate this with an example. So which intervals is this function f of x equals 1 over x continuous on? Well, we want to see where the jump is. And we can see that 1 over x is a special type of function. It's actually a rational function, which means that we have a restriction in the denominator. So the denominator can't ever be 0. And that's the only time that we really have functions that aren't continuous. Well, the ones that we're going to be looking at are all going to be rational. So where does this happen? Well, this happens when x equals 0. This function doesn't ever touch it, and that's actually going to be our vertical asymptote, if you remember that term from college algebra. So this is where the jump is. So this is discontinuous at x equals 0. All right. So where is it continuous? Well, it's continuous everywhere except x equals 0. Right? Because the curve goes on forever in the left direction, and it goes on forever in the right direction, and the only place that the x value doesn't cross is at x equals 0. And when we say interval, we mean x values, just to make that clear. So where is it continuous? It's continuous on the interval from x equals -infinity to x equals 0, unioned with x equals 0 to positive infinity. And notice that we're using parentheses where that 0 is because we're not including 0. Whenever we use brackets, we actually mean that we want to include that number. Okay, so that's our first example of a discontinuous function. Alright, let's look at this one. So this one we don't have an asymptote. We actually have what's known as a hole. So this is called a hole. And the function is discontinuous here. Basically what a hole means is that the function isn't defined there. And so basically there's only one x value that has a hole in it, and that's going to be x equals 3. So this happens at x equals 3. And so where is it continuous? The interval it's continuous on is everything except 3. So how do we represent that? We say -infinity all the way up to 3, union 3 to positive infinity. And again, we're using parentheses around 3 because we're not including 3. So that's where this function's continuous. So let's move on to continuity at a point. So what does that mean? Basically, if a function is continuous at a point, the nearby x values have corresponding nearby y values. Okay, so we just talked about the quadratic x squared. We know for sure this is continuous. We can always draw a U shape without picking up the pencil. Continuous. So what does it mean to be continuous? So what does it mean to be continuous at a point? At maybe say x equals 2. That's a point. Well, x equals 2 is right here, right? Oops, give me 1 second, guys. My alarm's going off. So x equals 2 is right there. And if we notice our table right here, nearby x values have corresponding nearby y values. Well, look at this. Our x values that are close to 2, all of these numbers are very close to the number 2. The corresponding y values are all very close to the number 4. And in fact, that is f of 2 equals 4. And so the way that we can see this graphically is we can draw a little neighborhood around the x value 2. And my neighborhood's going to look something like this. And so maybe all of these points on the table are around in that neighborhood. And then on the y side, we have a neighborhood around 4. So we have this neighborhood. And so what this is saying is that all of the x values that are close to 2 map to y values that are close to 4. And we can see all of these points that are in the table right here on our curve. Okay, so that's what it means to be continuous at a point. Okay, so what functions are continuous? So I kind of mentioned this a little while ago, but basically if you don't have a restriction on the domain, your function's continuous. So like anything like we have pictured here, all of these are continuous because you don't have to pick up the pencil. And you guys probably learned about these exponential functions, polynomials, sine and cosine in college algebra / trig. So exponential functions, so exponential, for example, we have y equals 3 times 2 to the x, okay? No domain restriction because x is not in the denominator, okay? We also have polynomials, which is like x squared, x cubed, 2x squared plus x cubed, stuff like that. So we could have 2x squared. Let's maybe do it like this. Let's do y equals 2x squared plus 3, or maybe y equals 3x to the 4th plus 3x minus 2. These are all examples of polynomials, okay? And then we have sine and cosine functions, which are kind of wave shaped. So like this graph right here in the top left corner, that looks like a sine or cosine function because it's periodic, it's wavy. And so all of these are examples of functions that are continuous. And these are going to be special functions that we can that we use when evaluating limits. And so that's why we're talking about continuous functions first, because yeah. Okay. All right, so rational functions are continuous anywhere except where their denominators are 0. Okay? So the first example that we have is the function 1 over x minus 2 continuous on this interval? Remember, this intervals are x values. So let's draw a little neighborhood around the interval on this graph. So this just came from Desmos. And so when x equals -1, that's about right here. When x equals 1, that is about right here. And so it looks like this curve, if we follow it from the beginning of the interval to the end of the interval, it does indeed look like it's continuous, right? So this part, yes, it's continuous on this interval. Another way to see it is that 1 over x minus 2, when we set x minus 2 not equal to 0, the only restriction that we have is x is not equal to 2. And 2 does not live in that interval. It's actually outside of -1 to 1. It's right here. Okay? So that's one way of looking at it. Well, yeah, so algebraically or graphically. So that's the first one. It is continuous on that interval because that interval does not include 2. But does this interval include 2? Well, yeah, it does. Because when, maybe I should do this in a different color. How about green? Let's do it in green. So if we start our little neighborhood at x equals 0, that's right here. And then our neighborhood ends at x equals 3, which is right here. So maybe I'll draw it on my curve, like that. And notice that to get from the left-hand curve to the right curve, we have to do a jump, okay? So this isn't one continuous motion. We have to pick up our pencil. So this is not continuous on this interval. And that's because 2 lives in that interval from 0 to 3. Okay, let's do another example. Is the function g of x equals 1 over x squared plus 49 continuous from x equals -7 to x equals 7? Well, -7, if we draw our little neighborhood, is going to be right here, starting. 2x equals 7 is going to be right here. And our graph of this function just looks like a straight line, right? It looks like it's getting super close to y equals 0, which does happen, right? When x gets really, really big, or even when x isn't big, this thing is going to get really close to 0, the whole function, 1 over x squared plus 49. So the graph tells us that it is continuous, but let's look at it algebraically. So we can obviously see from the graph, well, maybe not obviously, I shouldn't say that, but so the graph says it's continuous because there's no jumps. Algebraically, we take the denominator, x squared plus 49, and we say that it can't equal 0, and we solve for x. So we can subtract 49 from both sides and take the square root. But guys, we can't take the square root of a negative number. This is imaginary. This is imaginary. And for that reason, since we're graphing everything in the real plane, we don't have any excluded values. So this is going to be continuous on any interval, on any real interval, because there's no excluded real values. All we have is imaginary, and we don't really care about imaginary. Maybe later, but not now. Okay, so let's see. All right, let's look at a trig function. Those are always fun. All right, now we have this crazy graph, 1 over cosine of x. It looks like a bunch of like parabolas repeating themselves, and you can probably guess from the picture that this is definitely not continuous for all x values, because you do have to pick up the pencil. Like if you start at the leftmost parabola and just kind of like trace it off, to get to the next one, you have to jump. You have to jump like, from here to here. So it's already looking pretty grim. But what we want to do is we want to see what our excluded x values are. So we take our denominator, so algebraically. Let's do algebraically first, and then we'll look at it graphically. Algebraically, cosine x better not be 0. Can't have the denominator equaling 0. And guys, unit circle, it's back to haunt you. Where is cosine x equal to 0 in the unit circle? Well, at pi over 2. Remember this? The unit circle, the x value is cosine. So this happens at pi over 2, which means that our excluded value is pi over 2. X cannot equal pi over 2. And so the question is, does pi over 2 live in this interval? In between, no, that's not a negative. Well, the answer is yeah, because if you remember the unit circle, pi over 4 is right here, pi is right here, and pi over 2 is up top. So yes, pi over 2 does live between pi over 4 and pi. So the answer to this is no, it is not continuous on this interval because it includes an excluded value. So the answer, not continuous on pi over 4 to pi, because pi over 2 is in that interval. Okay, so let's look at this graphically. So we want to draw our neighborhood around pi over 4 and pi. Well, guys, we know pi, our upper bound, is about 3.14, so maybe 1, 2, 3, I don't know, maybe right here is our upper bound. And then pi over 4, let's just punch this in the calculator. Pi divided by 4, that is about, let's see. My calculator's given me 0.785, so a little less than 1, so maybe right here. That's our neighborhood that we're given. And you can see that this curve, let's start at so that's where the curve starts, and then it has to jump at some point, right? It has to jump to get to this one. And so we can see graphically that this isn't continuous in that neighborhood either. All right, so the reason that we're talking about continuity is because we're about to talk about limits. Now taking limits of continuous functions is the easiest thing in the world. And you'll see why, because it's basically just like evaluating functions that you've been doing in intermediate algebra and college algebra. But we need to talk about limits because not all of the functions we're going to be dealing with are continuous. Okay, so we need a way to observe what happens to a function near a point, and that is where the limit comes in. So this is the notation right here. The way that you read this is as follows. As x approaches a in the function f of x, or actually, let's read it like this. So as x approaches a, f of x approaches L. Okay? So that's what this means. The whole idea of the limit is this. We want to answer the question, let's see, how should I frame this? We should say, when x gets close to a number, what does y get close to? That's what this limit business is all about. So like, let's go back to this example that we looked at. This is about a limit. So if I ask you, what is the limit as x gets closer and closer to 2, that's what's representing, that's what's represented by this table right here. When x gets closer and closer to 2, as we can see, 1.9, 1.99, what's happening to y? The closer x gets to 2, the closer y gets to 4. Okay? That's the whole idea of a limit, and we're going to do plenty of examples, so don't worry. I know this is unfamiliar, and a lot of calculus students don't like limits when they first see them, but I'm going to try to make this as painless as possible. All right. So let's kind of just get some intuition about what a limit is. Okay? So what does this mean? We're trying to figure out what y value this function goes to as x gets close to 0. So let's write that in words. As x gets close to 0, what does y get close to? That's what this means. Now, if you notice, at x equals 0, the y value is undefined. There's a hole there, but that's okay. Holes don't matter with limits. They don't matter at all. All we care about is getting really close to when x equals 0. So what we do is we look at, we start at x equals, negative 1.75, and we get really, really close here from that side, and then we get really, really close to this x equals 0 on the other side. And what are these things converging on? Well, that's converging on a y value of 1. So that's my answer. The limit is 1. Okay, we're going to do plenty of examples. So that's our first taste of limits. Okay, so here's the formal definition of the limit. I'm not going to ask you to recite this. I like to talk about limits a little bit more intuitively, but this is it if you want it. And you can see with the picture, this is kind of what I've been explaining. We have this neighborhood around something that x is getting close to. In this case, it's a. And we want to see where y is getting close to, right? And to see where, what y value they converge on. Okay, so that's the precise definition. Well, it's actually not the most precise definition. There's a crazy definition involving delta and epsilon, but we're not going to talk about that in this class. If you take advanced calculus, if you're a math major, you're going to see this for sure, but in this class, I don't think we're going to get that deep into it. Okay, so the next thing we want to talk about, how do we get limits from a table? So again, I mentioned how to find a limit. We look at x values that are close to the number that we're approaching, and we plug them into the function. And I'm going to show you how to do this on Desmos, and the first thing I'm going to do is I'm going to write this function down so I don't forget it, and we're going to put this thing in Desmos. So you can just go to des.com. Hey guys, in the last video we left off with this problem, and so what I'm going to show you now is how to use Desmos to plug in a function and find the limit of said function. Okay, so the first thing we're going to do is we're going to copy this function, or write it down if you will, into Desmos. And so the way that we're going to put this function in is we're going to press the plus sign at the top left, and then we're going to click on table. Okay, so at the top you see x1 and y1. I'm going to go over to x1 and I'm going to delete that to just make it x. And for y1, I'm going to input my function. I'm going to put x minus 4. I'll do it in parentheses. So let's see. So I have x minus 4, and then that's all divided by x squared minus 3x minus 4. Alright, so there's my function. And now let's go back. So I want to evaluate the function at each of these x values to see what's happening when x gets really close to 4. So I'm going to input all of these x values into my table under x, of course. So we have 3.9. Okay, and then we have 3.99. 3.999. 4.001. You see the outputs coming on the right side. 4.01 and 4.1. So it looks from this table as the x values get really close to 4 on both sides, on the left and the right side of 4. It looks like this function is getting really close to 0.20. Okay, so we're going to guess that that's our limit here, 0.20. So the limit is approximately 0.20. As x gets closer to 4, y gets closer to 0.20. So that's our answer here. All right, let's do another example. This time we have a trig function, sine to the third of x over x to the third. So I'm going to do the same thing, and this time I have different x values because I want to see what y is approaching as x approaches 0. So I'm going to again put my function in my table by pressing that plus sign, doing table, changing this guy to x, and changing y1 to, we're going to put this in parentheses, sine of x to the third. That's the same thing as sine to the third of x. Okay. And we're going to divide this by x to the third. Alright. So now my x values, I'm getting close to 0, so I have negative 0.1 followed by negative 0.01 followed by negative 0.001, even closer to 0. And then I'm on the other side of 0, on the right side, at 0.001, 0.01, and finally 0.1. Alright, so the limit, it looks like, as x gets really close to 0 on the left and the right side, this y value is getting really close to the number 1. Okay, so that's going to be our limit here. So limit is 1. Alright, so now we're going to talk about taking limits from a graph. And so we need to define one-sided limits. We need to talk about the left limit and the right limit. So right here, I mentioned that the left-hand limit and the right limit when going to 0. So like when you're going to 0 for the x values, coming from the left, what you're doing is you're coming this way in the negative direction. So let's actually not put that right there. Oh. So these values are all coming from the left, these negative values. And these guys right here in orange, these x values are all coming from the right of 0, right? And they're approaching 0 in the middle. Okay, So in order for a limit to exist, the left and right limits must be the same. The left-hand limit is just the limit as x approaches a number from the left, and we denote it as follows, okay, right here. And so we have this little minus sign at the top as a superscript when we're coming from the left. In a similar way, when we're coming from the right-hand limit is denoted with this plus in the superscript. Okay, so the limit as x approaches a from the right of f of x is equal to L. That's what this says. And then up here, the limit as x approaches a from the left of f of x is equal to L. So let's look at a quick example. So let's look at this function right here, and suppose we want to find the limit as x approaches 0 from the left. And let's also say that we want to find the limit as x approaches 0 from the right of f of x. Okay, so coming from the left-hand side of 0, all the x values to the left of 0 are everything in yellow. So as x moves on from the left and gets closer to 0, what is f of x getting close to? Well, it's also getting close to 0. Right? So that's our limit coming from the left. Now on the right, we have a different limit. So everything to the right of 0 is coming from the right. We're getting closer and closer from the right, and we end up converging on this y value, which is 1. Okay, so the limit here is going to be 1. And since these two limits are different, then the limit in general, as x goes to 0 without any plus or minus signs, it does not exist because the left and the right hand limit are different. There's a jump. Okay. Let's do some more examples with this. Alright, so now we have a graph, piecewise function, and we're asked to evaluate all of these limits. Alright, so let's start with A. The limit of this function as x gets close to 0 from the left. From the left. Okay, so here's my function 0 from the left. These are all the x values that are to the left of 0, and we're getting closer and closer and closer to y equals 0. So the limit as x goes to 0 from the left is just, oops, that's right here, it's just 0. Okay. All right, let's look at part B. Now we're coming from the right. So as x gets closer and closer to 0 from the right, we start on this curve. That's to the right of 0. Get closer and closer, and we end up converging on this y value right here. Okay, so that's going to be a y value of 2, so that's our answer. And finally, for part C, since 0 and 2 are not the same number, the limit of 0 does not exist. In order for it to exist, A and B would have to be the same answer. Alright, let's look at part D. Now we're looking to see what the limit as x gets closer to 2 from the left is. So 2 from the left. Okay, well, let's see. Well, as x gets closer and closer to 2, there's a jump here. Okay, and then to the left. Okay. As x gets close to 2, it looks like our y value is converging here on negative 2. Okay, so that's going to be our limit as x approaches 2 from the left is negative 2. And as x approaches 2 to the right, from the right, what is it going to? Well, it's going to y equals 0. Okay, so again, this limit does not exist for the same reason that part C didn't exist. The left and the right hand limits are different. Okay, now let's look at the last one, which is 4. So we're trying to see to the left of 4 first. As x approaches 4 from the left. Okay, when do we stop? We're going to stop at x equals 4, which is right here. Okay, so what y value is that? That corresponds to a y value of 4, so that's my answer here. And as we get close to 4 coming from the right side of 4, again, the limit seems to converge on y equals 4. So this guy is 4, and therefore the limit as x goes to 4 is indeed 4. And notice that in the two cases where the limit does not exist, we have jumps, right? And that's going to be what happens every single time because it's discontinuous. In the first case, when we were going to 0, we have this jump right here. And then in the second case, when we're going to 2 from the left and the right, we have a jump right here, okay? So anytime we have a discontinuity like that, the limit is not going to exist. Now, this is asking, what is f of 0? Well, f of 0 is the value of the function when x equals 0. Well, there's two places where x equals 0, the closed dot and the open dot, but the closed dot is only where 0 is defined. We can throw the open dot out. Okay, so f of 0 is going to be 2. Now f of 4 is, so here's x equals 4, so happens on this open dot, which is undefined, and so f of 4 is also undefined. There's no closed dot to cancel it out. All right, so let's do another example. So now we're taking the limit as x goes to -2. All right, we have to check our left and right hand limits. So the first thing, we want to know what's the limit as x goes to -2 from the left. As x goes to -2 from the left, we're coming, and we converge on this y value of -4. It doesn't matter that it's undefined. Remember, limits, we don't care if what it's going to is undefined. Okay, so this answer is -4. Now let's look at the right-hand limit. The limit as x gets closer to -2 from the right. Okay, so this time we're coming from the right of -2. We're coming. And again, we're converging on y equals -4. And so the limit as x goes to -2 is equal to -4. That is my answer here. The left and the right hand limits are the same. Okay, let's look at what happens with -1.5. So let's see what happens when we come to -1.5 from the left. Let's see. So when we come from the left, -1.5, let's find out where that is first. It looks like, let's do it in green. -1.5, it looks like it's about right here. Okay, so when we approach it from the left, closer and closer and closer and closer from the left side, and we end up converging on y equals 0. Okay, so this is going to be 0. And again, from the other side, if we start coming, if we come from the right side to -1.5, get closer and closer and closer again to 0. And so the limit is 0 because the left and right hand limits are the same. All right, let's look at part C. This time we're going to x approaches 1. Let's do the left side first. All right, let's do the left side first. So as we get closer and closer to 1 from the left side, what's happening to our y value? Well, it's getting close to y equals 2. So that's going to be our limit of the left-hand side. Now, if we come from the right side, let's see what we get. All right, so we're getting closer and closer to the 1 from the right side, and we're getting close to y equals 0. So the limit coming from the right is 0, and therefore the limit in general does not exist because the left and the right hand limits are different. And we can see that there's a jump right here. There's a jump, what's known as a jump discontinuity right there. Okay, and the last one that we're going to look at, oh, never mind. We're going to see what happens when x goes to 4. So we want to look at the left and the right side. So when x goes to 4 from the left, let's see what happens. 4 from the left. All right, so the left of 4 is around here, and it's converging on this y value of 4 as well. So the limit of the left side is 4. Let's check out the limit of the right side. As x goes to 4 from the right. Okay, so coming from the right side of 4, get really close, and it looks like we're converging on y equals 6. So my left hand limit is 4, my right hand limit is 6, therefore the limit does not exist because the left and the right hand limits are different. Okay, shoot. Okay, the last one is to evaluate f of negative 2. So when x is negative 2, what is f of x? Well, there's actually 2 places, and which one are we going to take? We're going to take the closed dot, right? Because that's the only place it's defined, and that happens at y equals 3. So f of negative 2 is 3. And let's see. All right, let's go ahead and look at this one. So the limit as x goes to negative 4, well, from the left, it's going to 2. Okay. On the right, it's also going to 2. So this is going to 2 from the left and the right. Therefore, the limit is 2. What about x equals 1? So the left side of 1, it's converging on 4, y equals 4. But on the right side of 1, as we get closer and closer to 1 from the right side, it's actually converging on negative 2, on y equals negative 2. So therefore the limit does not exist because the left and the right hand limit are different. Okay, last example, when x goes to 6, what happens? So let's see. So when x goes to 6 from the left, x goes to 6 from the left, it's converging on 5. And when x goes to 6 from the right, it's also converging on 5. And so the limit is going to be 5. Okay. All right, guys, we are going to look at these last few examples in the next video. I hope this was helpful, and I'll see you guys in the next video. Thanks for watching. Hey guys, in the last video we left off on this example. We're going to kind of come back to continuity in terms of limits. And the first thing I want to do is talk about 3 examples of when a limit fails to exist. So the first one is the graph of the absolute value of x minus 2 over x minus 2, and we're looking at the limit as x goes to 2. And so we can see, just like in previous examples, that when x gets close to 2 from the left, f of x is getting close to -1, but when x is coming to 2 from the right, we're getting close to +1. And so in this example, the limit does not exist. Okay. We also have another example of the graph of 1 over x squared as x goes to 0. So we can see that since we have a variable in the denominator, this thing's going to be discontinuous at x equals 0. In other words, we have a vertical asymptote on this y-axis. And so as x gets close to 0 from the left, this thing is going to get bigger without bound. And so the limit here, y is getting close to infinity. And on the other side as well, as we get close to 0 from the right, y is also going to infinity. So the limit is going to equal infinity. And we only say that a limit exists when the function's getting close to a number. But infinity isn't technically a number, so the limit does not exist. DNE. Now this is kind of an interesting example. We have the graph of sine of 1 over x, and we want to see what happens when x gets close to 0. Well, we can see that in both cases, from the left and the right, that it seems like it's oscillating between -1 and 1. Right? So we have, here's x equals 0 right in the center, and we can't really pinpoint the value of what y gets close to, because it looks like y gets close to two things. It looks like it gets close to 1, and it looks like it gets close to -1 in both cases. And so for that reason, the limit does not exist here either. And the next thing we're going to talk about is the definition of continuity in terms of limits, now that we have limits under our belt. So the function f is continuous at a point x equals a if, first of all, x is defined at a, and second of all, if the limit of that function as x gets close to a is f of a. And for this reason, we can find the limit, let's write it down here, the limit of continuous functions by substitution. And I'm going to show you what I mean by that. So remember, we talked about continuous functions, what they are. Basically, if you don't have a variable in a denominator and if you don't have a radical, you can assume that the function is pretty much continuous if you're given an equation, or an expression rather. So for example, polynomial functions are continuous, such as this one that we have right here. And since that's the case, the limit is going to equal f of 3 by this definition right here. The limit as x goes to 3 of this continuous function is just f of 3. Okay, so all we have to do is plug in 3 for x and evaluate. Okay, so the limit is going to be 20, which is the same thing as f of 3. All right, let's look at the next one. Well, again, we have a continuous function. This is just a polynomial, -5x cubed plus 2x plus 6. We have no denominators to worry about, so we're assuming that this is a continuous function. And so now we're going to -1, so that's what we want to plug in for x and evaluate. Okay, so we have 9. So the limit is going to be 9 in this case. So let's talk about types of discontinuity. The first one we've seen in a couple of examples, and that's jump discontinuity. Basically, to get from one piece of the function to the next, you have to jump. Okay. We also have a removable discontinuity, and that happens when the limit exists at a point. So the limit exists here, but it's not defined at that point. Okay. Well, it is defined, but the limit does not equal what the function is defined as. So that's a removable discontinuity. And the final one is what we saw with 1 over x squared, and that's the infinite discontinuity. So that's in the case where we have a vertical asymptote. So as x gets close to a value, f of x gets either close to -infinity or positive infinity. So let's talk about where this function is discontinuous and using the definition. So you should refer to this definition when we're talking about this. We're going to talk about why is it discontinuous. All right. Well, the first thing we want to look at is we want to look for any holes that we have. And the first one we see is this one right here. Okay, so we have a discontinuity. Now, it turns out that we're looking at x equals -7, and f of -7 is equal to, looks like 4. However, the limit of this function as x goes to -7 does not exist. And that's because from the right side, it looks like it's going to y equals 2, but from the left side, it's not going anywhere. The curve's broken. And so for this reason, because f of a is not equal to the limit as x goes to a, because these are different, it's discontinuous at x equals -7. So that's our first discontinuity. All right, let's look at the second one. Now we have a hole right here, and it turns out that both from the left and the right, we're both going to this y value of, looks like it's at y equals -2. But what's the problem here with our continuity definition? The problem is that at x equals -3, this function is not defined anywhere. We don't have a closed dot right here or anywhere else, and so because it's not defined here, we can say that this is also discontinuous at x equals -3. All right, let's move on to the next piece. All right, so now we have this hole right here. And, well, it turns out that the limit, it's the same reason as the first one. Maybe we'll do this in red, actually. So the limit as x goes to, x goes to 2. Well, that limit does not exist because from the left it goes to f of x equals 1, and from the right it goes to f of x equals 2, so this does not exist. However, f of 2 does exist, and it equals 1. Okay? And because the limit does not equal f of 2, this is also discontinuous. So this is discontinuous at x equals 2. Oh, I think I erased this up here. This is x equals negative 3. So the red and the green are discontinuous for the same reason. Okay, now we have an asymptote. That's the last thing we need to look at. Is this guy right here. And that is x equals 4. So this is discontinuous at x equals 4. Because it's not defined there. It's not defined at x equals 4. Okay, and let's see, what else? Did we miss anything else? No, I think that covers it. So those are some examples of discontinuities and how to find them in a graph. Alright, so properties of limits. It's basically what you would think if you take the limit as x goes to a number p of f of x plus g of x, you can separate them with addition in the following way. And so I think the best way to illustrate these properties are just with a couple of examples. And so let's look at the first one. So we're adding these guys, these two functions. And so by property number 1, this first one, this is the same thing as the limit as x goes to 2 of x squared plus the limit as x goes to 2 of x to the third. And we know since x squared and x to the third are both continuous, we can just plug in 2 to both of these to evaluate. So the first limit is going to be 4, and the second one is going to be 8. 2 cubed is 8. And so our answer is 12. Alright, so multiplication, again, we can do the same kind of trick here. So this is the same thing by property number 3. This is the same thing as the limit as x goes to 3 of 6x squared times the limit as x goes to 3 of 7x. And again, 7x and 6x squared are both polynomials, continuous, so we can just plug in 3 for both of these guys. And so our first one, we get 6 times 9 is 54 times 21 for the second one. And let's see, 54 times 21 is going to give us 1,134. Alright, let's do the next one. So now we have subtraction. So again, we're going to use, let's see, this is property 2, the subtraction property. So we can separate it out again as limit as x goes to negative 2 of 5x to the 4 minus the limit as x goes to negative 2 of 2x. These two functions, 5x to the 4 and 2x, are continuous, so we can just plug negative 2 in for x in both cases. And we end up getting, let's see, negative 2 to the 4th is 16. 16 times 5 is 80. So we get 80 minus negative 4. So this is going to give us 84. So the next thing we're going to talk about are infinite limits. And I'm going to go ahead and make a new video for these last couple of problems. But yeah, thanks for watching so far. I'll see you guys in the next video. Hey guys, in this next part of the video, we're going to talk about infinite limits. So infinite limits, basically, it's kind of what you think it is. It's when the x value is approaching either negative infinity or infinity, what does the y value approach? Okay, so let's just look at a couple of examples, and let's start with this guy. And I'm just going to put this in Desmos and look at the graph. So we have negative x to the fourth. So there's our graph right here. So the first one is as x gets closer and closer to negative infinity. Well, it looks, if we keep scrolling down, as x gets closer and closer to negative infinity, it seems that y also gets closer and closer to negative infinity, right? We just keep going down. And so this guy, limit as x goes to negative infinity, is going to be negative infinity. All right. What about as x goes to positive infinity? Scroll back up. So as x gets larger and larger and larger, as x gets larger and larger and larger, y gets smaller and smaller and smaller. So y is also going to negative infinity here. So the limit as x goes to positive infinity is also negative infinity in both cases. All right, let's look at this function right here. 5 plus 21x minus 2x cubed. Make sure I have that in right. Alright, let's see what happens when we go to negative infinity first. So as x gets smaller and smaller and smaller, it looks like y is getting bigger and bigger and bigger. So when x goes to negative infinity, y goes to positive infinity. And when x goes to positive infinity, let's see. It looks like we have the opposite thing happening. When x gets larger and larger and larger, y gets smaller and smaller and smaller. And so the limit as x goes to positive infinity is negative infinity. Okay, so that's some examples of infinite limits. Alright, so now we're going to evaluate some limits at infinity. And there's a trick. So this is the first thing that we learned was with continuous functions, we can just plug in our values. Okay? But with infinity, since infinity is not a number, we end up getting infinity over infinity if we were to plug in infinity into any of these function values, right? And we can't have that. So we need another strategy. Infinity over infinity isn't always infinity. And so what we need to do is, the trick here is to divide top and bottom by the highest power expression. So in this case, x to the first is the highest power, so I'm going to divide everybody by x to the first. And remember, I can do this because dividing everything by the same thing is just like multiplying the fraction by 1. So I have x over x plus 3 over x over 2 over x minus x over x. Okay? Now, this guy goes to 1, right? This guy also goes to 1. And so what we're left with is 1 plus 3 over x over 2 over x minus 1. Okay, so now here's the trick. now we can talk about what happens when x gets close to infinity. All right? When x gets huge, what happens to 3 over x? Well, let's look at a graph. When x gets huge, what happens to 3 over x? Okay, so when x approaches infinity, look at what y approaches. Y approaches 0. As x gets really big, this thing goes to 0. Okay? Same reason for 2 over x. 2 over x goes to 0 because, again, as x gets huge, 2 over something huge is getting close to 0. And so what we end up having is 1 plus 0 over 0 minus 1 gives us negative 1. That is our limit here, okay? Negative 1. Now let's do another example. So this time our highest power expression is x squared. Okay, so we're going to divide everybody by x squared. So let's do that. So on top we have x over x squared minus 5 over x squared. On bottom we have 5 over x squared plus 2x squared over x squared. And now we can simplify this. X over x squared is just 1 over x. And on the bottom, we end up with just 2 right here because these guys cancel out. All right? Okay. So now on top, when x gets huge, 1 over x goes to 0. When x squared gets huge, 5 over x squared goes to 0. Okay, now let's go to the bottom. 5 over x squared goes to 0 when we plug in infinity for x, when x gets really, really big. And so we end up getting 0 over 2, which is 0. Okay, so the limit as x goes to infinity is 0. All right, let's do some more examples. Highest power expression looks to be x to the 5th. So we're going to divide everybody by that. Okay, so this turns into x to the 4th over x to the 5th plus 3x over x to the 5th. X to the 4th over x to the 5th. And then we can simplify. Okay, so this becomes 1 over x plus 3 over x to the 4th divided by 1 over x plus 2. Okay. Alright, so on top, as x gets huge, what does 1 over x become? It becomes 0. Same thing for 3 over x to the 4th. When x gets huge, this goes to 0 as well. On the bottom, as x gets huge, 1 over x goes to 0. 0 plus 2 is 2. So 0 over 2 is going to give us 0 again. All right, let's look at number 4. So I don't like negative exponents, so the first thing I'm going to do is actually rewrite this. 2 to the negative x, guys, is the same thing as 1 over 2 to the x. So I'm just rewriting this before I do anything. Okay, and on the bottom, I have 1 over 3 to the positive x. I just don't like negative exponents. Okay. All right, so let's look at this first expression. Okay. When x gets really, really big, what is this thing going to go to? Well, it's going to go to 0. Okay. And on the bottom, when 1 over 3 to the x gets big, this thing goes to 0. And so I'm just left with 5 over 7 is my answer. 0 plus 5 over 0 plus 7. So that's the limit as x goes to infinity. And my last one, x squared plus 9 over x plus 3. My highest expression is x squared. So I'm going to divide everybody by x squared to give me the following. X squared over x squared plus 9 over x squared Okay, now I can simplify, giving me 1 plus 9 over x squared over 1 over x plus 3 over x squared. Okay. Alright, on top, when x gets huge, this whole thing goes to 0. So I get 1 plus 0 is 1. On the bottom, both of these things, when x gets huge, go to 0. So on the bottom I get 0. We can't divide by 0, and so this is going to tell us that our limit as x approaches infinity does not exist. Alright guys, I hope this video was helpful. Thank you for watching, and see you next time.